Welcome to Civil Engineering Edge, where we dive deep into the world of innovation, infrastructure, and intelligent design. Today, we're stepping into the future of construction, a future that's green, smart, and sustainable. As climate change accelerates and global urbanization expands, the construction industry faces a critical question. Can we build without harming the planet? The answer is yes, and it's already happening. Around the world, engineers, architects, and builders are embracing green building technologies that are transforming how we design, construct, and live in our built environments. From eco-friendly materials to energy-efficient architecture, from 3D printed homes to smart cities powered by data and renewables, we are witnessing a powerful shift in how buildings contribute to both society and the environment. In this video, we'll explore four major segments shaping this transformation. 1. Sustainable building materials, the foundation of eco-conscious construction. 2. Energy efficiency and smart design, buildings that breathe, adapt, and save energy. 3. Innovative construction techniques, from robotics to modular construction. 4. Net zero buildings and smart cities, where the future of living begins. Whether you're a civil engineering student, a construction professional, or someone who dreams of building better, this video will open your eyes to the revolution in construction that's already underway. So stay tuned and get ready to see how civil engineering is not just shaping structures, but shaping the future of our planet. From concept to concrete, the future of construction is greener than ever. Watch this video to discover how civil engineering is redefining the way we live, work, and build. Let's embrace the change and shape a more sustainable tomorrow. Segment 1. Sustainable building materials. The backbone of green building lies in the choice of materials used for construction. Traditional materials like concrete, steel, and bricks, while strong and reliable, come with a significant environmental cost. Cement production alone accounts for nearly 8% of global carbon dioxide emissions, and mining for raw materials contributes to land degradation and biodiversity loss. As the world moves towards more sustainable development, the construction industry is adopting eco-friendly materials that reduce emissions, improve building performance, and promote a circular economy. One of the most promising materials is cross-laminated timber (CLT). Unlike conventional timber, CLT is engineered by layering wood planks in alternating directions and bonding them with strong adhesives. This process increases strength and fire resistance, making it suitable for large multi-story buildings. As trees absorb CO during their growth, using CLT not only stores carbon, but also supports sustainable forestry practices when sourced responsibly. Hempcrete is another rising star in sustainable construction. Made from the woody core of the hemp plant mixed with lime, hempcrete is lightweight, breathable, and offers excellent thermal insulation. It also absorbs carbon dioxide during the curing process and is naturally resistant to pests, mold, and fire. Moreover, hemp is a fast-growing crop that requires little water or pesticide, making it an environmentally friendly resource. Recycled plastic building blocks are gaining attention for their versatility and potential to tackle the global plastic waste crisis. These blocks, made from shredded plastic waste, are durable, lightweight, and interlocking, similar to Lego bricks. They are ideal for low-cost housing, disaster relief shelters, and community infrastructure projects. In addition, bio-bricks and mycelium-based materials represent cutting-edge innovations in biotechnology. Bio-bricks are grown using bacteria that produce calcium carbonate, mimicking the process that forms natural limestone. Mycelium, the root network of fungi, can be molded into panels, bricks, and insulation materials that are 100% biodegradable. By incorporating these materials into mainstream construction, the industry reduces reliance on non-renewable resources, cuts carbon emissions, and lowers energy consumption during both construction and the building's life cycle. These materials are not just alternatives, they are key components of a sustainable future. In summary, sustainable building materials offer durability, cost efficiency, and reduced environmental impact. Civil engineers and architects are increasingly prioritizing these options, not only to meet green building certification standards, but to pave the way for eco-conscious cities and structures that can thrive in the decades to come. Segment 2: Energy Efficiency and Smart Design. While sustainable materials form the core of green construction, energy-efficient design is what brings a green building to life. A structure is only truly sustainable if it minimizes energy consumption throughout its operational lifespan. In this segment, we explore how intelligent architectural planning, integrated technologies, and natural systems come together to create energy-smart buildings. At the heart of energy-efficient design is the principle of passive architecture. Unlike active systems that rely on electricity or mechanical parts, passive design focuses on the building's orientation, layout, and thermal behavior to naturally regulate indoor temperatures. For example, strategically positioning windows to capture daylight reduces the need for artificial lighting. Overhangs, shading devices, and thermal mass materials help in minimizing heat gain during summer and maximizing it during winter. This results in a significant drop in energy demand for lighting, heating, and cooling. Next, we have green roofs and vertical gardens living systems that serve multiple functions. They act as insulation layers, reducing the building's energy needs while also managing storm water runoff, improving air quality, and enhancing biodiversity in urban environments. These nature-integrated systems create microclimates that reduce the urban heat island effect, especially in densely populated cities. Smart energy systems are the next critical innovation. Buildings are increasingly fitted with automated sensors, smart thermostats, and adaptive lighting systems that respond to occupancy, temperature, and daylight availability. For example, smart HVAC systems adjust airflow and temperature based on real-time data, improving comfort while saving energy. LED lighting systems, integrated with motion sensors and daylight sensors, ensure that energy is used only when and where it is needed. Another transformative practice is the integration of renewable energy sources like solar photovoltaic PV panels, building integrated photovoltaics BIPV, and even wind microturbines. These systems generate electricity on site, reducing dependence on fossil fuels and contributing to a building's energy self-sufficiency. BIPV, in particular, integrate solar cells into building materials such as glass windows or facade panels, blending energy production seamlessly into the architecture. Water efficiency also plays a role in smart design. Low-flow fixtures, rainwater harvesting systems, and gray water recycling reduce water consumption and ease pressure on municipal water supplies. Sustainable drainage systems (SUDs) help manage runoff and reduce the risk of urban flooding. Together, these innovations represent a shift from static, energy-draining buildings to dynamic, intelligent structures that actively conserve resources. Civil engineers, in partnership with architects and energy experts, are creating environments that not only meet performance standards, but also improve quality of life for occupants, all while minimizing the building's carbon footprint. Segment 3: Innovative Construction Techniques. As green building gains momentum, it's not just what we build or how efficient a building is once it's completed, it's also about how we build it. Traditional construction methods are often time-consuming, labor-intensive, and generate excessive waste. In contrast, modern civil engineering is embracing innovative construction techniques that are not only more efficient and cost-effective, but also environmentally responsible. One of the most groundbreaking advancements is 3D printing in construction. This technique uses large-scale printers to extrude concrete, clay, or even sustainable materials like bioplastics in programmed layers to form walls and structural components. Entire houses can now be 3D printed in under 48 hours with minimal labor, reduced material waste, and greater design flexibility. This method is especially valuable in disaster recovery, low-cost housing, and remote construction scenarios. Another revolution in building is modular and prefabricated construction. In this method, building components such as walls, floors, or entire rooms are manufactured in a controlled factory environment and then transported to the site for assembly. This not only ensures high quality through precision manufacturing, but also drastically reduces on-site construction time and noise pollution. Modular construction is inherently sustainable. It minimizes waste, reduces emissions from machinery, and uses resources more efficiently. It's ideal for housing, hospitals, schools, and commercial buildings. Robotics and automation are also making waves in the construction industry. Robots can now lay bricks, tie rebar, pour concrete, and conduct repetitive tasks with speed and accuracy, reducing the dependency on manual labor and enhancing job site safety. Automation improves consistency in construction quality and allows projects to continue in adverse conditions where human labor may be limited. Another transformative tool is the use of drones and building information modeling (BIM). Drones offer real-time aerial views, site inspections, and volumetric analysis, enhancing project planning and monitoring. BIM enables all stakeholders, engineers, architects, contractors to collaborate on a digital 3D model that integrates data about every aspect of the building, from materials and design to timelines and cost estimates. BIM enhances coordination, minimizes errors, and supports sustainable design choices from the very beginning. Together, these advanced construction techniques reduce material waste, optimize resources, speed up timelines, and improve structural performance. They also make it easier to incorporate green design principles and energy-efficient systems into every project phase. In conclusion, the future of construction is automated, intelligent, and sustainable. By adopting these techniques, civil engineers are not only increasing productivity, but also aligning with the global need for environmentally responsible and resilient infrastructure. Segment 4: Net Zero Buildings and Smart Cities. As the construction industry evolves, the ultimate vision of sustainable development is not just individual green buildings, it is the creation of entire smart cities built around the concept of net zero energy. In this final segment, we explore how civil engineers and urban planners are working together to design communities and cities where energy production equals energy consumption, and where every component from homes to transport to utilities is digitally connected, efficient, and environmentally conscious. A net zero building is one that produces as much energy as it consumes over the course of a year. This is typically achieved through a combination of high-efficiency building systems, renewable energy sources like solar panels or wind turbines, and smart energy management. These buildings are insulated to minimize heating and cooling demands, use energy-efficient lighting and appliances, and integrate intelligent control systems to monitor and optimize performance in real time. Scaling up from individual structures, we arrive at the concept of smart cities, urban environments that leverage data, digital technologies, and interconnected systems to improve the quality of life for residents while minimizing ecological impact. Smart cities use real-time data to manage traffic flow, reduce energy consumption, enhance waste management, and monitor air and water quality. For example, smart grids optimize electricity distribution and storage based on demand, while sensors detect leaks or inefficiencies in water and sewage systems. An essential component of these cities is integrated transportation systems. Electric vehicle EV infrastructure, autonomous buses, bike-sharing systems, and pedestrian-friendly design reduce reliance on fossil fuels. Public transport is not only electrified, but also connected via apps that provide real-time updates, reducing congestion and enhancing user convenience. Water and waste management are also central to smart city planning. Net zero buildings incorporate rainwater harvesting, gray water recycling, and low-flow fixtures, reducing demand on municipal systems. Citywide waste-to-energy plants, recycling programs, and composting initiatives ensure that less waste ends up in landfills and more is converted into usable resources. Additionally, urban greening, including green roofs, vertical gardens, and expansive urban parks, improves air quality, mitigates the urban heat island effect, and promotes mental well-being. These green spaces also function as natural flood control systems during extreme weather events. In conclusion, the future lies in holistic, integrated urban ecosystems. Net zero buildings and smart cities are not just technological advancements, they represent a philosophical shift toward balance with nature, efficiency in resource use, and equity in urban development. For civil engineers, architects, and planners, this marks a new era of responsible design and digital transformation, where sustainability is embedded into the very fabric of city life. Conclusion and benefits. Green building and future-forward construction practices are no longer optional, they are essential for a sustainable tomorrow. Through our exploration of sustainable building materials, energy-efficient design, innovative construction techniques, and net-zero smart cities, one thing becomes clear: the civil engineering world is undergoing a powerful transformation. This isn't just about reducing environmental harm, it's about building smarter, living better, and leaving a legacy that future generations can thrive in. The benefits of green building are far-reaching. Environmentally, they reduce carbon emissions, minimize waste, conserve natural resources, and improve air and water quality. Economically, they lower operational and maintenance costs, improve building value, and support a growing green job market. Socially, they promote healthier living spaces, increase comfort and productivity, and create resilient communities that are better prepared for climate challenges. These innovative approaches are already being adopted around the world, from 3D printed housing solutions to fully digital smart city networks. Civil engineers are now not only builders of infrastructure, but also stewards of sustainability. The tools are here, the knowledge is available, and the future is being built brick by sustainable brick. If you're as inspired by the future of green construction as we are, don't forget to like, share, and subscribe to Civil Engineering Edge for more videos on innovative engineering, modern infrastructure, and sustainable design. Got questions or ideas for future topics? Drop them in the comments, we'd love to hear from you. Turn on the notification bell so you never miss a chance to explore of Civil Engineering Edge with us. Together, let's build a better world one smart, sustainable step at a time.